Good morning. I'm working on the KRT ecosystem and Sirius Polaris middleware. KRT is for the embedded systems. So it's a core, it's a kernel core, a real-time and a scheduler code for microcontrollers. And it has been ported to PIC16F, 628 and 876. Actually it needs to be completed, so how this works. We have this file, KRT core and user C file. In it stands the complete operating system, and we need to implement in the user file the drivers for communication, GPIO, things like this. And if you see the core, we have the RT and the schedule tasks. So we have for real-time and scheduled for 20, 100 milliseconds and a 1 second loop. These are the tasks. They run in interrupt or scheduled context. These are the places to implement the driver. For example, we see that for the 4 millisecond loop, we implement a fault and alarm LED on the actual microcontroller pin and the serial communication loop. And we can have the scheduled tasks or the real-time tasks. And we see that on the 1 second scheduled task, we also have a blinking LED, and we have the buffer for serial communication reception, and implemented the driver function putchar, getchar, and deal with the commands received from remote. In the main, we call the scheduler in the while loop. This runs the tasks, and this idle function collects system information called systat. Interrupt code is the core. We just have to start the 4 millisecond real-time in a timer loop, so that all the real-time functions are called in an interrupt context. And therefore they need to be very short, very efficient, and never slip over 4 milliseconds of CPU time, of course. And we can check that through the watchdog. So it was ported and working for PIC16F628 with about 1.066K of flash and 91 bytes of RAM, SRam. And that's the middleware, the SP software. And we have three components: the real-time embedded system, the middleware, and the UI UX. So the real-time system, the real-time kernel, runs on the microcontroller. The middleware runs on a Pi or computer and exchanges messages with the kernel, embedded kernel. And the UI runs on remote or same computer as the middleware, or any system that interfaces through UDP or sockets, unit sockets. So the kernel supports 8, 16 and 32-bit microcontroller, and that's the diagram for the connection. So we have the embedded board with a small microcontroller. In that case, I run a serial communication here. So it's a 19.2 kilobaud communication to both of these. Actually, the application and the middleware run on the main computer. So this is the middleware. I'm going to run it. Here we are. It's a version 10x. Has been built on yesterday. And we are disconnected and we are as a client. So now I'll go through connection. Okay, I'll go to the server. And the server in this context is always the remote. The client is the own computer itself, and the server is the remote control unit, embedded systems. So we see we're connected to the PIC16F that is running this code, and we will see all commands available. We see the help, so general commands. And then the server commands, we can run server run stop for the user task and the kernel task. The user includes the drivers. We can inquire for status, clear the fault, check the status, warning fault, gather statistics. We have GPIO manipulations for digital input, output, analog, PWM. We can set up according to what has been implemented in the driver. We can control the board. We have this example given here. To read a GPIO, write a GPIO. So we're going to check the the status, and we see that the microcontroller is actually running. We have no fault, no alarm. And we are going to gather the system statistic. This stats say that the average real-time load is 4%, and we have spikes at 65%. It says that the stack for the scheduler is used at maximum. We do again because we server systat, read back and reset. So we have the fresh value, and fresh value are 25% of the max load. So now if I make a stop, system statistic, we see overload on the stack, and status, we see that we have a fault. We see the stack load is high, and we see the stack for user and kernel are full. That's normal because we have stopped the kernel and user space scheduler, and so we see we have a fault, and indeed if we make a run, clear the fault, statistics, stacks are good now, no fault, no alarm, stack load is good, and that's now the correct value. And still we have a high stack load. That's because we have the previous value, we need to refresh them. And so that's the middleware, so this software can be interfaced to a web browser. The application side can be quite simple. We have these demo examples where we have a sensor talking to a microcontroller through GPIO and analog channels, analog signals. The MCU is running the KRT kernel. It has a serial COM. The middleware and the UI are running remotely. So in this case we have, for example, a Raspberry Pi for the middleware, a web browser. That is, this actual web browser shows the sensor application values. We have the same with a control light, open, close the door. We have exactly the same setup where we have the middleware and the UI or UX can be on the same computer. Like this, we have the back end. This is really talking to a hardware microcontroller. But these demo are examples. They are running simulations because all is not fully implemented. The purpose of the SP middleware is to provide sockets, UDP and Unix, for demo like this to run and to talk to the microcontrollers through this software, this piece of software. Then we can have readings of the analog channels, scaled. The same with a min-max recording and an average. We can do RLC measurement. If the board has the proper hardware support, then we can do simple things like this. We can do a simple dashboard and controls for the relays. We can do measurement and then calculate the diagrams. Precision measurement for resistor with a mean, standard deviation. Here we can do a motor system. So we always have the application talking to the local or remote middleware through UDP, through sockets, and the actual middleware that is here is translating the commands and reading back the informations to the application UI. And for the development purpose, we can do these kind of things. System monitoring, read the GPIO, configure, check, implementation of actual microcontroller tasks, so we can here have the readings of the GPIO, anything we need, record them, and then through the communication protocol with SP middleware, we'll get the information back from here. This project will be in GPLB3, the embedded C kernel, these files. Kernel core is short, is 1000 lines. The user code is depending on application. This one is 300 lines. The compiled application for 16F628 actually is just 1K of flash, 1066 bytes, and 91 bytes of SRAM. Thanks for your interest. Hope to see you later. Keep in touch. You will be able to check this project, get the boards programmed with a firmware, or just use the ports to program your own application. You just need a microcontroller basically, and a serial communication to the computer through Comptoire, for example, and then you can just use this demo application. For example, this one, to monitor the analog channels. And this one is very interesting. It needs a specific hardware to be able to have a precision measurement. And we get the fluctuation due to the stability of the signal and some perturbation on the signals. Thanks, and keep in touch. Bye bye.